Okay, so for this first problem, we're given a point A in the soil zone above the water table, and we're told that the metric suction is 0.60 meters. And just to be clear, just because we might sometimes want to work in centimeters, um, if we have that the suction here is equal to 0.60 meters, remember that there are 100 centimeters per meter, so this is equal to 60 centimeters. We can work either in meters or centimeters, but we need to pick one of the two. So to solve this, we'll write down the equation we're always going to use for head. Head equals z plus psi. This is actually a really easy one. We've already given psi. We're given the suction. The suction absolute value of psi is 60 centimeters, and so we can immediately write down, if that's the suction, then the metric potential is the negative value, negative 60 centimeters. Okay, so we're given this here, and the problem reduces down to figuring out what z is. And we're told now to use the water table as the datum. So that means we want the elevation of this point here relative to the water table. And so we actually want this distance here. Right, there's the water table, and it's above the water table, so z is going to be positive. And we can figure out the value of that number because the total distance from the surface to the water table is 100 centimeters, and from the surface down to point A is 60 centimeters, so this distance above the water table has to be 40 centimeters. So our problem is simply h equals, I'll do it in centimeters, 40 centimeters minus 60 centimeters equals negative 20 centimeters. Okay. You're good. Okay, so there's the first thing. What is the head at point A? It's equal to negative 20 centimeters. And the next question is water moving up or down between point A and the water table. Now, when you get a problem like this, it's basically a Darcy's Law problem where you're going to use the reality of Darcy's Law, that is, that groundwater is going to flow from high head to low head. So whenever you have a problem where you have to determine the direction of flow, you need to know the head at two different values. Now, we've just learned the head. We've just calculated the head right here at A. And now we want to know whether it's flowing up or down between A and the water table. So we need to now know the head at another point, which is on the water table. So we'll just call this point B. It's on the water table. And we need to figure out what is the head at point B. Now, when you're on the water table, there's going to be a temptation to immediately assume that the head is equal to 0 on the water table. But that is only true when the water table is the datum. And remember that whatever the datum is, you have to use the same datum for every point you measure in that problem. Now, in this particular problem, we're using the water table as datum, but I'm going to show you shortly how we could have solved this problem using another choice of datum and gotten exactly the same answer. So in this particular example, B is on the water table and the water table is datum. So the head at B, we're going to use the same equation, H, I'll do it in red here, right? H is equal to Z plus psi. Remember, too, that psi in general is equal to P over rho G. This is always true. So what is the elevation at the water table? Well, if the datum is the water table, then this is 0. And what is psi on the water table? Well, we have to calculate it, but it's a really easy calculation because along the water table, by definition, the pressure here is equal to 0. And so if the pressure at the water table is 0, then psi will always be 0. The metric potential at the water table will always be 0. So in this case, where datum is the water table, the head at the water table is going to be 0 plus 0, or 0. So now we have our head at 2 points. And we'll write them in. Let's write them in a different color here so we can know what we're doing here. So write them in green. Give me a chance to do this green. Okay. So the head here at the water table was 0. The head at A was equal to minus 20 centimeters. So which is the higher number? 0. So therefore, groundwater will be flowing from higher head towards lower head in this direction. In other words, it's flowing upwards. Now, let me just get rid of all this stuff and just show you how we could have solved this exact same problem using another choice of datum. I know that's not what the problem asks, but I think it's very instructive. So let me get rid of all this crap and we'll start again. Okay, sorry for my sloppy erasing here. Okay, let us now assume, instead of having the water table as datum, let us now assume that, let's make the datum the surface of the ground. So here is now my new datum. This red line, this is datum. And we're going to solve the exact same problem using a different choice of datum. And we better get exactly the same answer. So once again, we'll just do it more quickly here. H is equal to Z plus psi. Right? We've been told already that the metric suction here is equal to 0.60 meters. Let's do it in meters this time, okay? And so therefore, the metric potential is equal to minus 0.60 meters. So now we can use the fact that H equals Z plus I. We've already got this figured out. We need to figure Z out. Z now, however, is the surface of the ground. And so we can see right here that A lies 60 centimeters or 0.60 meters below the surface of the ground. So in that case, Z will equal minus 0.60 meters. Minus 60 centimeters minus 0.60 meters. So the head here now at point A will equal Z plus psi, which is equal to minus 0.60 meters, and minus another 0.60 meters equals negative 1.2 meters. All right. Okay, so there is my 1 point. We'll do that in green. So we know the head here now is equal to minus 1.2 meters. Okay, and just again, we have to figure out what the head is at the water table so we can figure whether water is flowing between the water table and A, up or downward. So we have to pick another point. We'll pick it down. Where'd it go here? Pick a point. We'll do it in a different color. We'll do it in red. So pick a point here. Okay, there's point B. So the head at B will equal Z plus psi. Now, for the arguments I made last time, psi is always going to be 0. Psi at the water table is always 0 because the pressure at the water table is always 0. The elevation head, though, is not always 0. Now we've chosen datum to be the surface of the ground. So in this case, this elevation, Z of the water table, is not 0. But what is it? Well, it's 1 meter, 100 centimeters or 1 meter below datum. So Z is equal to negative 1 meter. And so the head at B, at the water table, is equal to negative 1 meter plus 0 equals negative 1 meter. I'll write it over here. So head here equals negative 1.0 meters. So again, now we can answer the question, which way is groundwater flowing? It's flowing from the head at the highest value, which is negative 1, towards an even lower value, negative 1.2. So once again, it's flowing up from the water table towards point A. And notice additionally that I didn't show it, but the difference in head is exactly the same in both cases. It's 0.2 meters. We're always going to get that answer regardless of what we choose as datum. But, and super important, we must calculate the heads at both points using the same datum.